The particle in a box has been a useful exercise here, and now we can extend these ideas to the harmonic oscillator to see how it too can give us oscillation. We're going to start off with a simple example. Just like the particle in a box example, we can look at a superposition of the first two energy eigenstates. This is quite straightforward to write down and quite simple to understand.
Quite generally, if we're looking at superpositions, if we make a linear combination of two energy eigenstates with energies EA and EB here, the resulting probability distribution is going to oscillate at the frequency, the angular frequency, EA minus EB, and we can take the modulus here to get a positive frequency, over h bar. This is the frequency at which the oscillation will take place. So if we have a superposition wave function of one particular function in space with its energy and some coefficient Ca here, and another function in space with its energy and some coefficient Cb here, this is just a linear superposition of two states, then the probability distribution, by the same algebra as we've just done, will be this expression here, Ca squared times this probability density, Cb squared times this probability density, plus this oscillating term here that oscillates at the energy difference over h bar frequency. Also, we have an angle in here, which is technically what we'd call the argument, the angle corresponding to this particular complex number here. And that can vary in space in this particular case. But the basic form is the same as we just saw. So with the harmonic oscillator, we can work this out. And as a reminder, here is what the harmonic oscillator wave functions and energies looked like for the first two states. So the energy of the first state relative to the bottom of the parabolic potential was h bar omega over 2. The energy of the second state was h bar omega over 2 times 3, in other words, 1.5 h bar omega. And this omega was the oscillation frequency, the angular oscillation frequency of the classical oscillator with the same potential. So as we said, here are the wave functions, one with one bump in it, one with two bumps in it. So qualitatively not so different from the particle in a box problem. And again, in this case, we've been plotting them with these orange dashed lines as the horizontal axes in each case. So here's our n equals 0 in this case, the lowest energy state, with the wave function now plotted with the horizontal axis here being the height equal to 0 axis. The bottom of the potential well is where we've drawn our horizontal axis for the wave function now. And here's what the probability density looks like, the modulus squared of that function. It's the same kind of shape, but it's just narrowed up a little bit. And again, if we were to multiply this function by its time-dependent factor and take the modulus squared of it, the modulus squared, the probability density, is the same whether or not we multiply by the time-dependent factor. It makes no difference. The measurable quantity is the same for this eigenstate whether we multiply by the time-dependent factor or not, just as before. Similarly, we can plot now the n equals 1 function, which is the second one in the harmonic oscillator problem, and it goes down and up and back. And again, we've chosen this as our horizontal axis now. And similarly, we can work out the probability density, again very similar to the particle in a box problem qualitatively. It's all positive, of course, and it's got two bumps in it. And again, if we multiply the spatial eigenfunction by the time-dependent factor so that it becomes a solution of the time-dependent Schrödinger equation, it makes no difference to the probability density. An equal superposition of these two states is going to oscillate. And it's going to oscillate at the angular frequency here, the difference between the lowest energy and the energy of the next state, which here are called E0 in the harmonic oscillator, n equals 0, and E1 for the next state up. And as I said, we'll get an oscillation at this angular frequency. And of course, here's the expression that we've just worked out, and here's the oscillation term down here. And here's what happens. So we're plotting here the sum of the two waves, then modulus squared, which is what we have to do in quantum mechanics. And we're seeing this oscillation here that goes on. So again, the particle is sort of oscillating between the left and the right and back again. It's a slightly complicated looking little pattern in here, but we're certainly seeing an oscillation between the right and the left and back again. And it's oscillating at this frequency omega, which is, in this case, also the frequency of the classical harmonic oscillator with the same potential. So our omega here, E1 minus E0 over h bar.
So now we have at last seen the harmonic oscillator oscillating, and at the frequency we were expecting, namely the frequency of the classical harmonic oscillator with the same potential energy function. However, the behavior we are seeing here is still not very close to what we typically see in a classical harmonic oscillator. In our next segment, we will see how to get that behavior, real harmonic oscillation, from a quantum mechanical oscillator.